Looking at some nice work by social scientists who worry about adaptation gaps, and the practical aspects of adaptation, whereas the climate community is there making their scenarios, projections, predictions, and climate scientists are always convinced that better predictions are going to save the world. So these people always raise good questions. Do we need better predictions to adapt to a changing climate? Many scientists have called for a substantial new investment in climate modeling to increase the accuracy, precision, and reliability of climate predictions. Such investments are often justified by asserting that failure to improve predictions will prevent society from adapting successfully to a changing climate. This forum questions these claims, suggests limits to predictability. There are irreducible uncertainties in the system, no matter how much data you have, and so on. For example, the impacts of aerosols on cloud formation, cloud brightness, cloud rainfalls, droplet sizes, and so on are probably always going to remain highly uncertain with irreducible uncertainties. High knowledge doesn't mean lower uncertainty in those cases. They argue that society can and indeed must make effective adaptation decisions in the absence of accurate and precise climate predictions. So the example I always mention is the sea level rise. For example, a city like Mumbai. What can it plan for? Does it really matter whether it has a very precise sea level rise prediction, or is it going to be ultimately determined by what it can afford to do, right? Or even what people are willing to do in terms of moving away from the coast. This is a big issue in large parts of the US, for example. People want to live near the coast, and they don't care if more cyclones are coming, more sea level rise is causing problems. And we know from past historic evidences that societies don't get knocked off only with one big hit. They need to be hit again and again and again before they take big decisions or they go extinct. This is something also that is part of human behavior. In the meantime, these are nice constructs which show the system uncertainties and the stakes that are involved in the decisions that have to be made in under uncertainty. Okay, so here is applied uncertainty when there is low decision stakes and low system uncertainties. Professional consultants try to translate the system uncertainties for you into what decisions you must make, like let's say your investor who is taking your money and telling you exactly how he's going to invest, and they have of course a horizon over which they say, look, I've been giving you 10% returns on 10 years. So you cannot jump up and down when you have big ups and downs. And then there is the idea of PostNormal Science, where system uncertainties are high, unacceptably high, irreducibly high, and so on, and decision stakes are high as well. So the climate models have to produce reduced complexity information in a timely fashion and with some sense of what they are depicting, what uncertainties come with them. What are the what-if scenarios covering in terms of what society will face? So science needs controversies to grow, as we said already, and hiding those from the public is not necessarily a good thing. So is consensus good for science? Obviously not. So there are three paradigms of uncertain risks. There's a deficit view, where uncertainty is provisional. To reduce uncertainty, we make ever more complex models, and the tools rely on quantification, these experiments called Monte Carlo and Bayesian belief networks and so on, which I won't go into in this course. Evidence evaluation view, where comparative evaluations of research results are made, and the tools include scientific consensus building, which is what is happening in climate change. Everybody's saying extreme events, sea level rise, intense hurricanes, Greenland ice sheet, Antarctic ice sheets are all serious issues. Complex systems view, or post-normal view, argues that uncertainty is intrinsic to complex systems. So this is again about saying, is climate change really unique, or have we always faced weather and climate related risks? Right? So it's intrinsic to the system itself. Uncertainty can be a result of production of knowledge. So you are actually amplifying the uncertainty by using scenarios, making projections. So there, you don't know the uncertainty quantification very well. Acknowledge that not all uncertainties can be quantified, right? Like the Greenland ice sheet or West Antarctic ice sheet. Openly deal with deeper dimensions of uncertainty like problem framing, indeterminacy, ignorance, assumptions, value loadings, institutional dimensions, etc., with tools being knowledge quality assessment and needs deliberative negotiated management risks. So what is normal and post-normal science? This is going back to the 1960s, where normal science is basically what we do usually, uncritical puzzle solving within an unquestioned framework of paradigms. So you have, let's say, astrophysics with its theories of the universe, black holes, star formation, supernovae, etc. And what all scientists do most of the time, and most scientists do all the time, right? This is, let's say you are trying to predict monsoon. You are going to just stick to the normal science in that case. Elements of post-normal science, on the other hand, include appropriate management of uncertainty, quality and value ladenness, plurality of commitments and perspectives, internal extension of peer community, so involvement of other disciplines, like if you're producing projections for a decision maker, it could be policy maker, it could be insurance companies, it could be communities, businesses, etc. You involve them in co-producing the information. External extension of peer community, so involvement of stakeholders in environmental assessment and quality control. So you define the value of what you're trying to protect in terms of what the community values and what they want. So they might say, we don't care if certain species disappears, let's say. Okay. So in that case, your model has to take that into account, at least in terms of where you're going to put your energy in improving your projections or predictions, right? So those are the issues one has to deal with when it comes to how useful predictions and projections actually are. They cannot be produced just by a group of climate modelers with input from integrated assessment models, and then integrate forward and then put them out and hope it gets used.